So welcome to lecture 27th, or the last lecture in this semester. So in this semester we have more lectures than usual. So thank you for your cooperation during this semester. Okay, so in lecture 27, we will finish the discussion about circuit analysis. After that, just briefly sketch how can you solve the device simulation with the transient capability. Okay, so I hope that we can finish it quite a short time. So in the previous lecture, we have discussed about Backward-Euler scheme for time discretization. So we assume uniform time discretization. After that, every quantity, so this is solution variable, a list of solution variable, and its time derivative is approximated. This is an approximation due to the Backward-Euler scheme, and this is present value, and we have no idea about them. And this is past value, and we have full knowledge on it. So we just take the present value minus past value and divide it by amount of time difference. So you will find that this is actually corresponding to a crude form of our certain variable and time derivative. So x at present time, x at past time. Yes, so when we take the limit of vanishingly small time derivative, then eventually we will get the real derivatives. Of course, this is not possible, so we will have a certain finite number for delta t, but we assume that this delta t is small enough to satisfy the closeness between this time derivative and its discretized form. And yes, then let's go to our real circuit implementation. Then let's go to our system. So we had a really simple RC circuit, and previously we had the terms like d over dt over our entire solution vector, but now that is approximated as just a difference between our unknown vector and its past value. So here you can see that when we take it, then this becomes the entire system equation. So previously, for example, related with this term, so this second law, we had minus c and positive c for this part. However, now we have 1 over delta t, 1 over delta t. Then previously we had time derivative term, but there is no longer time derivative term. Where is it gone? So now it is expressed in terms of our current values, now present values. And in addition, we have certain terms related with the unknown variables at the past instance. So please note that it is an unknown variable. However, this red colored vector, this is fixed or given. Previously we tried to solve it, but once we solve it, it becomes just a given vector. So you know that this is just a number. Number, 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 number. Therefore, you know, here for a given time instance, yes, this is a number, 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 number. They are not unknown. And quite similarly, this matrix is a given matrix, and this vector is also given. So our system now becomes extremely simple. So all of them, all of terms except for this one, this guy and this guy becomes just a given vector. We can just put it here, then everything can be written as our matrix, system matrix, so shaded here, and our unknown variable, yes, yes, equal to all of a certain given vector. So then by solving this system, yeah, then we can get the solution, this one, and that will determine your unknown variable at present time instance t equal to t sub I. Yeah. So that is quite a simple way to solve this transient problem. So yes, we have spent quite a long time about that, but the main message is quite simple. Yes, when you have a time derivative, just to express it as a difference between present time value and past time value, then the past time value can be regarded as a given constant. So that will contribute to your residue vector. That does not contribute to your Jacobian or unknown variable. Then your Jacobian will be slightly modified. Why? Because previously you had only the Jacobian obtained from this term, but now you have certain corrections taken from the time derivative. So you have slightly modified Jacobian matrix and slightly modified your residue vector. Then after solve modify the system, then you will get the solution for entire system. So we will make a really short discussion about transient device simulation. So this is the main discussion about the transient capability. So now let's go to the MATLAB implementation. For example, we can specify R and C and frequency. Then you can set up your system matrix. So please have a look at this second line once again. This second row contains this term. This term is really obtained from steady state Jacobian matrix. However, you can also find this term and this term. These terms are coming from your transient term. So time derivative term contribute these two terms. Also, let's go to your residue vector. And residue vector previously only cosine omega t. That occurs because we have a time varying signal for our voltage source. But as you can see here, our implementation also contains terms like this. What is it? This term is nothing related with voltage source, but it has certain relation with old solution. Here old solution means that the previous solution and the previous solution. So from the previous solution we can construct a modified residue vector, and by solving this modified system matrix and modified residue vector, then we will get the solution. Oh, but one more thing is, now we have the loop for time instances starting from 1 to n. Our time is increased, so t equal to delta t, t equal to 2 times delta t, t equal to 3 times delta t. We are marching to what? N times delta t. Then every time when we switch to the next time step, the present solution becomes the old solution. So when we try to solve the t equal to 2 times delta t, then the values at 2 times delta t, for example, this one is really unknown variable. However, if we try to solve t equal to 3 times delta t, then now we are interested with 3 times delta t quantities. And how about this? Then this one should be regarded as the past solution. So here you can see that one important line. So here we just copy the present solution to the old solution. So now we are switching to the next time point. So without this one, without this line, then you will not have the proper operation of your transient simulation. As you can see here, compared with this simulation, what is the key element to make the big difference between the steady state solution and transient solution? That is quite straightforward. So system matrix is also modified. That is one thing. Also, the residue vector is modified. That is also one thing. So these two makes difference in your result when you perform the transient simulation within short time period with a large bias damping ratio. Okay. Then you are now looking at the typed RC.M. So here I have set R and C values and frequency. Frequency here we have 1 kilohertz, so 10 to the 3 hertz, and system matrix, and you can find everything as before. And here I just store my solution into global solution or history of all our simulation result, and I will just plot in this figure 1 the data 4. What is data 4? The fourth data is corresponding to input voltage, and in figure 2 I will draw the third one. So this is register current. Okay, so then let's have a look at RC. So this is the result. So how does it look like? This one is our cosine function. So you can see that from the beginning of our time transient, we have 1, and yes, we have transient simulation, the signal corresponding to cosine omega t. And here you can see that, how does it look like? In this case, our solution is nothing related with cosine-like behavior. It is just sine-like behavior. It is because we are working with a relatively low frequency. Then let's go to high frequency, like 1 gigahertz. Then what will happen to this system? So let me just type it again. The input signal is the same as before, and now this is the output signal, and as you can see that now they become in phase. They are in the same phase because since this is a relatively high frequency, so now it becomes just so impedance of our capacitor becomes quite small. So now it becomes just a resistive circuit. So that's the reason why our input signal and output signal has the same phase. This is really simple code, but think about this one. It contains the essential ingredient of transient simulation. Although its solution vector has only 5 entities, but you can easily expand it to 1,000 or 10,000 and 100,000 quite easily. There is nothing more difficult than this program in transient simulation. So if you are working with transient simulation, this program can be used just the backbone of your all of transient simulation. Let's go to our last slide. So this will be the final slide for in this semester. We are now going to the device simulation. Then where can you find the time derivative terms in our device simulation? You can only find the time derivative terms in your continuity equations. So this is just the intermediate form, and you solve this round n over round t equal to 1 over q times divergence of Jn. So also you solve this equation. This is electron continuity and hole continuity. Previously, you have neglected these terms with a magic word like a steady state solution. However, now you have to consider them. Then how can you solve it? Now these two terms, okay, for example this one, for a certain position, let's say that you have a certain index for your position. So let's say that this is J is the spatial position, spatial index. So J is node, you have answer of J, and you wanted to calculate the round t at time instance equals t equal to k times delta t. Then how can you discretize this term? In this case, you can discretize it by and sub j at a given position. You have the present value which is included in your unknown variables, and minus nj which is calculated at k minus 1 times delta t. And as I told you before, this is once again already known function, known value. You know it and you don't know it. This is unknown. So please think that you have to solve this quantity, and this is given. Yes. So now your continuity equation can be modified as delta t n minus n past value. So this term contributed to your residue vector, and this term contributed to your Jacobian matrix. The only thing you have to keep in mind is you solve the integrated form of your continuity equation. Just to calculate round n over round t is not sufficient. You have to multiply the control area of your system. Yeah. So that is one thing you have to keep in mind. So with this, you can get the transient simulation result. Okay, then are you happy? But unfortunately, there is one thing we have to be careful when we calculate the IV characteristics. You have to develop or evaluate the displacement current. Displacement current does not play any role when you actually calculated the solution. When you calculate the solution, then you don't have to care about displacement current, because you should solve this Poisson equation. However, when you calculate your terminal current, you have to be careful. You should calculate this displacement current. Without this displacement current, you have no current conservation. So current conservation strictly holds when you include your particle currents and then the displacement current. So please be careful when you calculate your terminal current. Okay, so I see that is all for the entire semester.